equation in terms of the complex number and also complex exponential equation. Okay, so there are 4 basic, okay, for that you have to know about the complex number and also complex exponential. Okay, first is the common notation that we use is that the definition of I, which is I is actually equal to square root of -1 or I squared equal to -1. Okay, some books they will use J. Normally mathematician they will use J, but in this course I will choose I. Okay, and then number 2, the standard form of a complex number is given by Z equal to A plus IB, which is A and B are both real numbers, which is they are the real parts and imaginary parts. So for real part is the A and for the imaginary parts is B, which is they have the I before B. And then the complex conjugate of a complex of that equation, which is given by I Z star, which is equal to A minus IB. Okay, so if Z, we have that Z equal to plus, so different is here. Okay, so that's we call as a complex conjugate. And then the sum of the complex number, which is Z plus Z prime or Z star is equal to 2A. Okay, so this is the always real because A is the real number, which is there is no more I notation I here. So this is the always real. Then the complex exponential functions. Okay, so this is important. Okay, it's defined by E I theta is equal to cos theta plus I sine theta. So theta is any numbers. So I can put here as E I x. Then it goes to cos x plus I sine x. And the same, the conjugate of the complex exponential is given by the difference is here. So for the complex is become minus. Then this is the complex exponential of a function is defined in precisely the same way for the example of the function of f as a function of t for some arbitrary function of time. Therefore, now we replace the fft in the theta here. So your function will be like this. And as usual, for the complex, it's become like this. Okay, here actually we missing of the minus here. It should be have the notation minus. Okay, it's the complex of this function. Okay, so the presence of the sine and cosine function is the complex exponential suggests that a connection with the simple harmonic motion. It is the method of the straightforward algebra to make it this connection explicit. Okay, as you know, okay, in simple harmonic motion, you have learned, okay, about the general solution, okay, for the equation of the simple harmonic motion, which is that equation is given by x as a function of t equal to a sine omega t plus pi naught, and then the general solution is given by this x double dot is equal to minus omega squared x. Okay, so here A and pi naught are constants that related to the initial condition, and also omega is the intrinsic property of the system under studies. Okay, so you have go through a few examples on this. Okay, so from here we can turn this equation in terms of the function of the complex function. Okay. So we will do it now. Okay, we write this solution by expanding the sine and sum of the angles omega t plus pi naught. Okay, so the equation is here, and then that is the sine omega t plus pi naught. Then when you expand this using the trigonometric identity, then it is equal to sine omega t cos pi naught plus cos omega t sine pi naught. Okay, so now that the x equal to a sine omega t plus pi naught is again it is equal to here, and you can rearrange this in such a way using this. Okay, so you put that sine omega t here, then this is the cos of sine pi naught, and this is here is the cos pi naught. And then because we can we define that ei omega t is equal to cos omega t plus I sin omega t, and the same of that conjugate. So now omega t replace theta as you have at above. Okay, as this. Okay, so now what you we going to do when you adding these two equation, okay, this equation 1 and equation 2, then the answer we have that ei omega t plus e minus I omega t is equal to 2 cos omega t, because this will be cancelled out. Okay, and then our purpose here, we want to replace here. So now this part will be the title, which is here. So we want it here. It's not 2 omega or t, but we just want that cos omega t. Okay, so this is a 2, you will be bring here, and then we will be like this. Okay, then do the same thing, that subtract that equation 2 from equation 1, and then the answer will be here. Okay, then after that replace, okay, in this substitute, okay, what you have into this equation, and then finally we have this answer after you factor out. Then you arrange the equation, and then finally we can define as a xt equal to b ei omega t plus b star ei omega t, where b is equal to this or equal to this in this bracket, and this is the for the b star. Okay, so you can have that xt is the sum of the complex function of b ei omega t and its complex conjugate, and xt is still a real function of time. Okay, or we can put as this. Okay, just now we just proved that this is equal to this. Okay, so our equivalent way of writing the general equation to the solution of motion, which is x double dot equal to minus omega squared x, that defines a simple harmonic motions. Okay, the two form of the solution are connected to their constant as given by this for B. Okay, other than that, okay, so this is the derivative of the exponential function. Okay, so here we recall the fact that all derivative of function x alpha t, where alpha is the numerical constant, is either real or complex, are proportional to the function itself. Okay, so both b and alpha constant are both possibly complex. The several derivative of u with respect to t. So here I will give up to 3. Okay, so you can look through this. Okay, now only we go to the real topic of this, okay, which is the Deng oscillation. First, we discuss about the general equation and solution. Okay, up to here we have concentrating to this point on the case that the net force on the object and system is a restoring force, which is that one we discuss in simple harmonic motion with a magnitude that is either exactly or approximately, which is in the case of the pendulum, it is as a near a stable equilibrium, which is this is the condition for simple harmonic motion to happen, and proportional to the displacement from equilibrium, that we have this as a equation of motion, which is x double dot equal to minus omega squared x. Okay, and in terms of forces, that we have that restoring force, okay, is equal to ma or mx double dot, which is equal to minus m omega squared x. Okay, so we have seen that the solution to this equation of the motion equal to this, okay. at t equal to a sine omega t plus pi naught, and we just shown that it is equivalently to this, okay, in terms of the complex function. And also we have proved that previously in previous lecture that we also seen that the energy, okay, the total mechanical energy, which is the sum of the kinetic and also the potential energies, is conserved in the system, and it is equal to half m omega squared a squared. Okay, but in reality, of course, the total mechanical energy of the system in motion is never perfectly conserved. Okay, so there is always some loss of the mechanical energy, perhaps due to the effect of as example of the internal friction, air resistance, fluid velocity, and so on and so forth, which is it then dissipated as a heat, for example. Okay, so due to this, while understanding a simple harmonic motion or simple harmonic motion, oscillation, the conservation of the mechanical energy and constant amplitude, it is important starting point for many physical analysis, the simplest version of the problem that we have started with a necessarily an idealization. Okay, so the system is the ideal. Okay, in the context of the simple harmonic motion or SHM, we refer generically to a resistive force which works to dissipate the mechanical energy from a system in motion as a damping force. Okay, so now you made the new term which is called as a damping force. Okay, this force, okay, generally is the velocity dependent, which is faster motion through air implies that the greater air resistance. Okay, the simplest possible dependence is one in which the magnitude of the damping force is just directly proportional to the speed, or given by magnitude of x dot, okay, which is the velocity or speed. Okay, so thus we have that the equation of the damping force is equal to minus gamma x dot, okay, which is here the damping constant. Okay, which here the gamma is the damping constant, and the unit for the damping constant, you can see that here that F has a unit of N or Newton, X or the velocity has the unit of meter per second, and so the unit of gamma is given by Newton per meter per second, which is also is equal to this, or it is normally we give in term of the kilogram per second. Okay, so you can see here we have that the minus sign here indicates that the damping force always oppose the instantaneous motion. This slightly different from that restoring force, okay, which is m omega squared x for the force in the pure simple harmonic motion. In that case, the restoring force is always directed oppositely to the instantaneous displacement from the equilibrium, but the force, which is the acceleration, and the velocity will be in the same direction whenever the object is ready moving towards the equilibrium position, that is for half of the every cycle. Okay, the net force on a would-be oscillator subject to a linear damping force is the linear in velocity is simply the sum of the damping force plus with the restoring force. Then now you can have that this is the equation of motion for the damped oscillators, which is m x double dot equal to minus gamma x dot, which is due to the damping force, and m omega naught squared x here is the due to the restoring force. Okay, note here that the subscript of naught here or here on omega naught has been introduced here to denote that the angular frequency that would obtain in the absence of the any damping of the system, does not refer to initial value of omega naught, since this is just a constant. So this is to differentiate here is the for the undamped angular frequency, okay, or we call as a natural angular frequency. Okay, then from here, okay, we bring in all terms to the left hand side, okay, in this equation, and dividing through by the mass leads to the basic equation governing the motion of the damped oscillators. Then therefore you will have this. Okay, put this side and divide by m, and then you will have that x double dot plus gamma over m x dot plus omega naught squared x equal to 0. So this is actually the equation of motion for damped oscillators. Okay, as what you have in simple harmonic motion, the equation is that x double dot equal to minus omega squared x. But now for damped oscillator, you have the extra term here, okay, which is due to the damping force. Okay, now we stipulate that after we have this equation, and then we have to find the solution for this equation. Okay, as what we did for simple harmonic motion. Okay, so we stipulate that the solution xt to equation 4.3 for a damped oscillator, okay, for this equation, in the form of x alpha t times another function of t, which we call as a capital xt, okay, or the solutions will be small xt is equal to exponential function of e alpha t multiplied with capital xt. Okay, so now our job is to find the solution for this. Okay, it will be complicated, okay, compared to simple harmonic motion. Okay, so we're going to do this. Okay, it's already 10:30. We have that. I try to finish this, okay, before 11. Okay, so it is the general, completely general. We can always rewrite any arbitrary function in this way as the product of two other function. Okay, so by writing that small xt equal to e alpha t capital xt, we mean to isolate that the all factor out any and all exponential time dependence from the full solution of xt, and then to deduce what, if any, other form of time dependence might be left in the new function xt. Okay, you will see how we will do this. Okay, so starting from the definition of equation 4.4, okay, we can use that the change rule and the product rule of the differential together to find the derivative of x and x dot and x double dot in terms of derivative of the new function of capital xt. Okay, so small xt is equal to dx over dt. Okay, so back to the function here, st is here. Okay, so you can see that this is two term, one term and another term here. So that's why you have to use the change rule. I hope all of you familiar with this. Okay, so this is simple mathematics. Then finally, we have these two terms as an answer for x dot. Okay, and do it the same, okay, for that x double dot, which is d squared x over d squared. So you have to differentiate towards t from these two terms of x dot. Okay, so replace here. So you can see here 1, 2, 1, 2 terms. So all together is 4 terms. Okay, so do it slowly, use the change rule, and finally we have this as a answer for x double dot. Okay, so now we can use equation of 4.4, 4.5 and 4.6 to substitute for x dot and x double dot in equation 4.3, hence writing it in terms of exponential and the new function of capital X. Okay, so refer back. Okay, this we want to find the solution for this, and we stipulate the solution as is this. Okay, so what we're going to do is that we already find what is xt here, what is x double, what is x dot here, what is x double dot here. Okay, so after you have that, okay, and we have to we have to substitute back into that equation. Okay, so this is for x dot t. Substitute what you have. We found that for x dot t and for x double dot t, then multiply with this. Okay, from here you have this, and also the final one is xt. Then this is the answer for this, and collect all together. Then finally you have this, then factor out of e alpha t. Okay, I repeat, okay, how we can get this. First, this is the solution or the motion equation of the damped oscillation. Okay, so we have the SR term here, which gamma is the damping force. Okay, so then after that we stipulate the solution as this, and what you have to do is that to find this, you have to find x dot t based on this equation, and also x double dot t. After we got this, substitute back into this equation, okay, for x dot, and also x double dot. So here is the answer. Okay, after we substitute, and this is the final answer after we factor out the factor of this. Okay, so as expected, the factor of e alpha t can now be cancelled from the equation, leaving an equation for the new function of capital x t only inside the square bracket for equation of 4.7, which must itself always 0. So the whole equation equal to 0. So this must be 0, and in this square bracket also is 0. So you can see here now there is no more small x in this equation, left only for the capital X. Okay, so now we're going to concentrate in this square bracket. Okay, moreover, since we introduced the definition of x, small x equal to e alpha t capital X in the first place entirely for our own convenience, we are free now to specify the constant of alpha in terms of the original physical parameters. Please be on time, because when you come late for the online class, you disturbing, okay, others. Okay, and in any way that makes it easier for us to go further in obtaining the full solution at t. Okay, so evidently we choose the alpha in such a way that we have this. Okay, and then the term in the xt vanished from inside the bracket in equation 4.7, leaving us with the equation that involves capital x double dot and also capital X dot, and it is easier to solve as this. Okay, and you can have that this is the quadratic equation. Okay, so this is the solution. So we have two solutions here, alpha equal to this plus and also minus this. Okay, so this gives us to the two possible of the constant alpha in the exponential parts of x. Xt equal to e alpha t capital Xt, and further implies that equal to this. Okay, so now we're going to have that three cases of this. Okay, so please don't be worried for this. I will not ask you, okay, to how to show all of this, or I will not ask you how to prove to get this solution. This is the way that how to show you how we can get the solution for damped oscillation. Okay, as long as you understood, okay, how to get this is enough. I will not ask you how to derive this. Okay, there are three different types of motion, okay, depending on the whether the properties of the oscillators in equation happen to make the quantity for this, okay, which is gamma squared over 4m squared minus omega naught squared is appearing under square root in equation 4.10. Please off microphone. Okay, to all students, please off microphone. Itu adalah salah satu. Okay, because you disturbing. Okay, we have about 20 minutes. Okay, So I hope, because now I think we already lag behind, okay, what we propose to do. Okay, so whatever it is, I have to finish this lecture by today. Okay, please give your cooperation. Okay, thank you. Okay, so what we consider is this square root. Okay, so now this is very important, which is this, we consider the cases, it will be 0, positive or negative. Okay, which is this alpha gamma squared over 4m squared minus omega naught squared. Okay, so for the case 1, so this is equal to 0, which is to be as a 0 that gamma or damping constant is equal to m omega naught. Okay, so this is we call, it is fall under category of the critically damped. Okay, so to remember this is easier when it is equal is the critical. Okay, so it is the critically damped. And one more thing I want to emphasize here is that, okay, when you want to categorize this is under critically damped or case 2, okay, we have the over dam, and the last one you're going to have the under dam. It is the comparison, okay, for the gamma and 2 omega n squared. Okay, please bear in your mind that gamma must be in the left side and 2m omega naught is in your right side. If you put in another way, it will be different. Okay, so for equal, it's okay for if you fall under critically damped, but when gamma is greater than 2m omega naught, it will be the over damped. Okay, and if less than it is, we fall under damped. Okay, so please remember that gamma must be on the left and 2m omega naught on your right. Okay, so for this case, we can have this, you can read through this. I will not go detail on this. Okay, the solution for here. Okay, again for this one also, I want to show you how to get this, but of course I will not ask you how to prove this solution for this case. So for case 1 is this the critically damped, so the solution for this, okay, you need to use the integration here, and we define as the constant C1 and C2, and then the final answer solution for this is that the xt is equal to minus omega naught t e minus omega naught t multiply with that C1t plus C2. Okay, so this is for critically damped. So remember that if you have that C1 and C2, C meaning critical, this solution for critically damped. Okay, so this represents non-oscillatory behavior, a periodic motion in which a displaced oscillator opposite equivalent 0 x equal to 0 exponentially at late times. Critical damping allows for the fastest possible returns of a displaced oscillator to equilibrium. Okay, for this part, we're going to touch this in lecture 7. Okay, so okay, and then for case 2, if that gamma is greater than 2m omega naught, this fall we call as a over damped, or sometimes they also call as a heavily damped. Okay, so for this case, it involves the new constant here is the q squared, which is equal to gamma squared over 4m squared minus omega naught squared greater than 0, and also alpha 1 and alpha 2 is equal to this. Okay, and then the final solution for this, we have 2, okay, because since we define that here we have the alpha 1 and alpha 2, so we have the x1 and x2. Then to find the total or the final solution, of course you have to add up these 2, and this is the final answer for this. Okay, so this is the, we have that the constant of B1 and B2 for over damped, where Q is equal to this. Okay, so this is the explanation for this. This also the non-oscillatory behavior. So this also we're going to touch this in lecture 7. Okay, so case 3, the last case for this is that when gamma is less than 2m omega naught. Okay, for this case, if less than, it is fall under damped. Okay, or sometimes it's called as a lightly damped. Okay, so this we're going to introduce the new positive constant as equal to this. Okay, and also involve the alpha 1 and alpha 2. Okay, and finally that the general solution for this is given by this. Okay, and remember here they use that V1 and V2 also, and so now this is the solution for the under damped oscillators. Okay, so the displacement oscillate. Okay, so this they show the oscillatory behavior. Okay, because you can see that here it's involve the sine function. Okay, it's compared to another two cases. Okay, so the displacement oscillate about the equilibrium of x equal to 0 with a period of t equal to 2 pi over omega for gamma as given in equation 4.16. A damping force in the underdamped case works essentially to make the amplitude of the oscillation decrease steadily over the time friction of any similar force remove mechanical energy from the system, and we know that E total is proportional to A squared. Okay, because we know that E total is equal to half m omega not omega squared A squared. So it is proportional to A squared. So A must decrease along with that E total. Okay, so this is the conclusion before we go to the example of this. Okay, so, but as usual, the example here without the solution, but we're going to discuss, okay, the solution for this. Okay, so it's a bit different because we do it as online. Okay, normally we discuss in the class for the solution. Okay, so but we have to get used to the new normal now. Okay. Okay, the conclusion for this topic. Okay, first we call to obtain the solution, we first define a constant alpha and a function of xt such that a small x is equal to E alpha capital xt, and then after some algebra, we stipulate that this equation, which is this is the second order differential equation, you can see that this is the square here to facilitate a complete solution. Okay, then secondly, what we did that, notice that the solution for equation x in equation 4.13 for critically damped, okay, when gamma is equal to 2m omega squared. Okay, in equation 4.14 for overdamping, which is when gamma is greater than 2m omega naught, and in equation 4.16 for underdamped when gamma is less than 2m omega naught, or involve two independent real constant, which is C1 and C2 for critically damped. You can find that in equation 4.13, B1 and B2 for critically damped, and for the only one that show the oscillatory behavior is the A naught and alpha naught is for the under damping. Okay, this always come from outside the original equation of the motion, where the only constant appearing are fundamental properties of the physical system. You can see that you can find this in the equation of the motion for damped oscillation. Okay, but they are all constant of integration. Okay, so they are exactly two independent constant. You can see that all of the equation 4.13, 4.16 and 4.14, or it is the two independent constant. You have that C1, C2, B1, B2 and also A naught and alpha naught. Okay, in the case of, because the underlying differential equation being solved in a second order equation. Okay, so it is logic. Okay, why we have that two independent constants. Okay, the value of the constant need to be inferred from any specific application of two independent pieces of specific information about the state of the particular system at some particular time, which is with the initial condition given, as what you have done in the example of the simple harmonic motion, which is you have to find what is the value of A, what is the value of gamma, and also what is the value of A, omega, and also what is the value of pi naught. Okay, that three constant we can determine using the initial condition given by the problem. Okay, we have about 10 minutes, okay? So I will give you the equation. Please write down the answer, okay? If we have time next week, okay, where we meet again in the Google Meet, I will give detail of the solution, okay? So, but then you, after your test, okay, you might try whether your answer is correct or not. Okay, a damped oscillation or a damped oscillator with a damping constant of 12 kilogram per second has the equation of motion of x double dot plus 6x dot plus 25 x equal to 0, where x is the displacement from equilibrium measured in meters. Okay, so the question already told you this is the damped oscillators. Okay, the question is, what are the mass and the natural angular frequency for this oscillator? So they ask for A, they ask you to find what is M, what is omega naught. The second, or B, what type of damping is this? So means that they ask you, they fall under which case? Case 1, case 2, or case 3, which is the critically damped, it is the overdamped or underdamped. Okay, and what is the oscillation period? So they ask you to find what is T. Okay, so all of this you need to do. Okay, as usual, how we solve the simple harmonic motion, how to find the solution for this, we need to refer back to the basic equation of the motion of damped oscillation, where this is given by equation this equation. Okay, so with this equation, you can compare with the equation given by the problem. Okay, please take note that you need this equation 4.3 equation, and you need to compare this with this equation. Okay, then through this you can determine what is M and also what is omega naught. Okay, please take note, I will give the answer. The answer for M is equal to 2 kilogram. Okay, the answer for omega naught is equal to 5 per second. Okay, I repeat, the answer for M is equal to 2 kilogram. The answer for omega naught is equal to 5 per second. Okay, then what type of damping is this? Okay, as I mentioned, okay, in case 1, 2, and 3, to know that what is the damping type we fall under which case, you need to compare the value of gamma on your left and the value of your 2m omega naught on your right. And the notation in between them that determine whether this is fall under critically damped, over damped, or under damped, critically damped, under damped, or over damped. Okay, when it is equal, okay, when it is equal, then it is the, when equal, it is the critically damped. Okay, and so on so forth. You can check back to the notes, okay, which is you need the value of gamma and you need the value of 2m omega naught. Gamma, as I told you, you can compare this with the equation 4.3. You can determine m, and also you can determine omega naught. Okay, then I already give to you m, the answer is 2, and omega naught is the answer is 5, and damping constant here already give to you 12. Okay, then you can compare that 12 with the 2m omega naught. So you can determine what type of damping is. Okay, this, for this I will not give you the answer. Next week when we meet again, I will ask you what is the answer for this. Okay, what is the oscillation period? Okay, you know that the period, okay, T is equal to 2 pi over omega. Okay, So please remember here, you find in this is the natural angular frequency, which is omega naught, but this they need the oscillation period of this system, which is you need to find first what is omega. Okay, it's not omega naught. Okay, you need to find first what is the omega. The answer for omega is 4. Okay, 4 per second, and therefore we have that your t is equal to 2 pi over 4, and the answer is 1.571 second. Okay, you got it? Okay, that's it. This is the answer. Okay, so with that, I think just nice, already 10:55. Okay, so you need to do a test at 11. Okay. Okay, the answer for B, I will give to you on next week. Okay, next week again, we will going to make here, and also, yeah, the test is from 11 a.m. until 12 p.m. So please do it as soon as possible before it end of the 12 p.m. And then after it close, you cannot send your answer, or you cannot submit your answer. So please submit your answers through Spectrum, but somehow as what you did for online quiz 1, some of you cannot submit due to the internet connection. Okay, so due to the internet connection, so because of that, I also accept you can submit that through email to me. Okay, but then please not later than 12 p.m. If not, I will deduct some marks, because the question is very easy. Okay, you actually already, if you did your tutorial 1, actually you can copy down your answer already. Okay. Okay, that for test, okay, from 11 a.m. to 12 p.m. Okay, today, which is 1 hour. Okay, and then for next week, okay, which is week 8, on 11 May, okay, you're going to have another online quiz 2. Okay, on online quiz 2, similar to last week, you have that online quiz 1. So the time only half an hour, and you need to answer NCQ questions. Okay, 4 questions. Okay, similar that you have in your online quiz 1. Okay. So I think that's all for today. So please do your test, and we meet again in next week. Okay, thank you so much. Okay, good luck for your test 1. Okay, stay safe. Okay.
Okay, thank you, Doctor.
Okay, thank you.